An exoplanet is a planet around a star other than our sun. But it turns out that there are about 2,000 exoplanets that are known in the universe. So there are thousands of planets known, but almost none of them are the size of the Earth. There's a strong bias to detecting larger planets, and especially large planets in short orbits. The bulk of them were detected by Kepler. It measures transits, it measures the slight dimming of a star as a planet goes across the disk of the star. You measure those a few times and you can confirm that there's a planet there. The rest of the planets were discovered by radial velocity, which measures the motion of a star toward or away from you as it reacts to the motion of the planet in its orbit. If you want to detect the light, it's very, very faint relative to the star, so there's a huge problem of glare. So the technology that I'm talking about is technology for going to space and being able to detect the light directly from a planet like the Earth, but we want to be able to put a slit across that image of the planet and then detect spectral features. Once you detect spectral features such as oxygen or water or methane, you begin to compare them to models and decide whether or not you think you're seeing signs of life. What we have to do is suppress the starlight glare around the stars so that we can see planets very close in. There are two ways to do that. One is called a coronagraph, which is an instrument inside the telescope. It blocks the starlight, but it lets the planet light through. The other is called a starshade. The idea is to put a screen out in space and block the light of the star before it has a chance to get to the telescope. A starshade is this disk. It's going to be about 34 to 40 meters in diameter. It's going to fly roughly 50,000 kilometers in front of the telescope. The idea of flying that far away is that it has to look so small that you can see the planet just adjacent to the star. So here's an example in the lab. This is a half-scale inner disk. It's based on what's called astromesh technology, which is, if you're familiar with this SMAP spacecraft, it's the same technology, it's slightly different geometry. We made it thinner and made it more compatible with holding pedals. So there's some really neat technology development going on in this area. The other way to observe planets is through a coronagraph. And the idea now would be, instead of having a second spacecraft and waiting a week to do these observations from one to the next, you have an instrument inside the telescope and you can just point from star to star as you would for any other kind of observation. But what you've done is you've let the light into the telescope. And once you've let the light into the telescope, you've hit these imperfect optical surfaces. So now we need to have a very complex system within the telescope to control that scattered light. First thing you have to do is be able to control the wavefront. So are there high precision deformable mirrors that we use? The next thing is that you need to take this controlled wavefront and focus it onto masks, either in the pupil or in the image plane or both. Next technology is the wavefront control itself. You have to be able to sense the wavefront, you have to be able to feed that back to the deformable mirror and control it. This chronograph that's being developed at JPL now is going to fly in space roughly in the middle of the next decade in the WFIRST mission. WFIRST is primarily a mission to study dark energy, and there's another experiment on board to do microlensing of planets. The chronograph will also be present. It will do direct imaging, it will do spectroscopy of Jupiter size and perhaps Neptune size planets. So those are the main technologies that we're developing for this quest for looking for life around other planets.